Welcome back to Mathora. If you loved our first video on related rates, you're going to love this one even more. Today, we will dive deeper with new real-world examples to really sharpen your skills. Whether it's measuring how fast a shadow grows or how fast water flows into a tank, related rates have you covered. Let's jump right in. Why practice more related rates problems? Well, related rates are everywhere, from physics and engineering to even sports. Whether you are tracking how fast two objects move related to each other or solving complex motion problems, this concept is super important. Mastering related rates will make you a calculus problem solving ninja. Alright, let's break it down with some new examples. Okay, let's move into our first example. It's growing shadow example. Okay, let's start with a classic problem like this. It's about a shadow. Okay, let's read it out. Imagine a 2 meter tall person is walking away from a street light that's 5 meters tall at a speed of 1.5 meters per second. How fast is the length of their shadow increasing when they are 4 meters away from the street light? So as the step one, we need to draw this one. Then after that, we need to identify the variables using the like by looking at this. So first of all, I will draw it for you, then you will understand. So as you can see, this is our street light, and this is the person who's 2 meters tall, and this is the shadow. Okay, this is the shadow, and that's the length for the shadow is going to be in L, and this is X. That means the distance between the street light and from the man, and it's going to vary from time to time, and L even also going to vary from time to time. So to identify this better, I will draw like this. And let's hope like this angle is something like alpha. And if this is like, then you can draw it like this. This is L, this is X, and this is 5, and this is 2 with the same angle. So you can see here we are having two triangles, but starting from a same angle. So we can write the relationship like this. Like normally, uh, we can see like if like the corresponding sides of like the division between the corresponding sides of each angle is equals to each. So we can write like this. 5 divided by x plus L is equals 2 divided by L. You got it? Because 2 divided by L is belongs to the small triangle, and 5 divided by x plus L is related to the larger triangle. So now we have the relationship. Now we need to simplify this equation. And we need to isolate L because we are going to find the answer regarding L. Because they're asking how fast is the length of their shadow increasing when they are 4 meters away from the street light. So you can write like this, 5L 2x plus 2L, and it's going to be 3L 2x. L is 2x divided by 3. Okay, as the next step, we need to differentiate with respect to time t. So we can write, I will write it here, TL over dt equals 2/3 is going to be a constant, so we are going to keep it like this. times dx over dt. Okay, now we need to substitute values. When the question is asking when x is 4, as you can see, how fast is the length of their shadow increasing when they are 4 meters away? That means x equals 4 meters. X equals 4 meters. And at a speed of 1.5 meters per second. So that means dx over dt. The rate of change of velocity is simply can be say as dx over dt. So, or maybe the velocity that's going to be 1.5 meters per second. So now we have the data. Now we can substitute them. So as we can substitute like 2/3 times 1.5. So the answer is going to be 2 times 1.5 divided by 3. It's going to be 1 meters per second. 1 meters per second. So the shadow's length is increasing at 1 meter per second when x equals 4 meters. Simple, right? Okay. So now let's try something different. Okay, let's move into our second example. Okay. Air is being pumped out of a spherical balloon at a rate of 50 cubic centimeters per second. How fast is the radius shrinking when the radius is 10 centimeters? So the radius means is about this. Like as you can see here, this, okay, I will draw the cross-sectional part. It's about like from this circle, it's the place that those air blows out from the balloon. So that's what they are telling here. So it's the radius r. So now let's solve this one. So before that, we need to write the formula for the volume of a sphere. So, oh no. Oh, I think I made a mistake here. I think you will also think you also thought like this way. So it's not going to be like this. So in here it's like I think they are telling about the radius about this. I think so. If not, we can't solve this question. Yeah, because it's asking how fast is the radius shrinking. Shrinking. That means about this radius, not about this. I think I made a mistake. Yeah. Okay. Now we know we have made a mistake. It's all right to make mistakes because from mistakes, that's when you are going to learn. Okay. So it's okay. Even I also did a mistake and I beg your pardon if I made you confused, right? Okay. Now we need to write the formula. It's going to be volume of a sphere, right? So V equals 4/3 times pi r to the power of 3. Okay, now we need to differentiate with respect to t. dv over dt is 4/3 times pi times this is going to be 3 times r to the power of 2 times dr over dt. As you can see, you can remove this 3 and this 3 by dividing each other. Then it's going to be dv over dt equals 4 pi t, sorry, 4 pi times r to the power of 2 times dr over dt. So now we need to isolate dr over dt to find these values. So we can write it like dr over dt is equals dv over dt divided by 4 pi r to the power of 2. Okay, as we all know, I'm sorry. Air is being pumped out of a spherical balloon at a rate of 50 cubic centimeters per second. That means dv over dt equals 50 cubic centimeters per second. And they are asking about the f- the speed of the radius shrinking when the radius is 10 centimeter. Then that means when r is 10 centimeters. Now we have our data. Now we can substitute them. So it's going to be 50 divided by 4 pi. R is going to be, it's 10, right? Yeah, it's 10. This is 10 cm squared. This is going to be 5 cubic centimeters per square. Yeah. So, okay, now we need to solve this. So it's going to be like 50 divided by 4. It's going to be 12.5. 5. Wait. 50 divided by 400. Yeah, I think, yeah. Or if not, to make it like a more clear answer without going into the more simplest decimal points, you can keep it like this. It's better, I think so, to make it more clear. So it's going to be like centimeters per seconds. And yeah, you don't need a calculator to solve this one. Yeah. So it's going to be 1 over 8 pi centimeters per seconds. So the radius is shrinking at approximately around 1 over 8 pi centimeters per seconds. So, and I want to tell you one thing. Here I didn't as get the dv over dt as a negative value, because actually it's going to be negative because in here volume is actually decreasing from the balance. So therefore dv over dt is actually a negative value. Because of that, dr over dt also going to be a negative value. But anyhow, in this scenario, I only considered about the mathematical value. So uh, keep it that in your mind too, right? So next time when you're solving the questions, you need to think about that one too. But in that scenario, I was only using the mathematical part only to show how to do it. Okay. So, okay, now let's recap this one. So step one, use related rates to connect changing quantities through equations. And step number two, differentiate with respect to time using implicit differentiation. And step number three, substitute known values to find the unknown rate. And so here, I'm going to give you a pro tip. Always pay attention to the units and whether rates are increasing or decreasing. It makes a huge difference. That's it for today's deep dive into related rates. I hope you feel more confident solving these kinds of problems now. If you loved this video, smash that like button, subscribe, and ring the bell for more awesome math videos. Let me know in the comments if you want me to cover any specific related rates problems next. As always, keep practicing, keep solving, and I will see you in the next one. Bye bye.